Papa, how are baby crocodiles made?
Well, you see, son, when a mama crocodile and a papa crocodile love each other very, very much, they don't actually need each other. Hi, today's video is going to talk about this recent paper called Discovery of Facultative Parthenogenesis in a New World Crocodile. We're going to break down what that term even means because parthenogenesis is super, super interesting. Classically, we know that sexually reproducing organisms need a male and a female of the species in order to pass on the genetic material to the next generation. However, we have been finding more and more species that exhibit parthenogenesis. That is the virgin birth. That is not needing two individuals from different sexes in order to produce an offspring. And it has been already noted in a wide variety of taxa, and more with time. So it has been noted. Let's actually go right back to the paper because no point in, oh gosh, good golly gee, hold on. Let's go right back to where we had it. Look at that. It has been seen in sharks, rays, sawfish. It's been seen in birds, other reptiles. I believe there was a recent news story of a reticulated python that exhibited parthenogenesis. And again, it is widespread across the animal kingdom. And it's very, very likely, or practically guaranteed, that it is underreported in the literature, meaning there are many, many more species that we know of that exhibit parthenogenesis, and we just have not found it yet. Now, this paper does go a little bit in depth about common characteristics of parthenogenesis. So some of the characters they mention are genomic imprinting, which is where genes are differentially silenced based on the sex of the organism. The sex of the parthenogens would be the offspring that is the offspring that is born from parthenogenic birth, is constrained by the species sex chromosome system. So in humans, we are XY organisms, meaning that if the offspring develops and it has inherited a X chromosome and a Y chromosome, it develops into a male. If it inherits two X chromosomes, it develops into a female. There are other organisms with a ZW system, which is basically in reverse. If you have heterozygous inheritance, so XY in this case would be ZW, you would then develop into a female, where the homozygous, the X, in our case XX, in this organism ZZ, would develop into the male. So basically our system just in reverse, and there are some really cool frogs that they buck all the rules with this. We'll talk about that a different day. Anyways, other characteristics are the capacity to switch between sexual and parthenogenic modes, ability to produce both types of offspring within a single reproductive event, the capacity for repeated parthenogenic events, and the reproductive competence of adult parthenogens, with both sexual and secondary parthenogenic events documented, basically meaning can the offspring mate and also exhibit parthenogenesis as well as sexual reproduction. So many of these characters are just, can they do it and do they do it repeatedly? But there are some really interesting traits that are common in those species that exhibit parthenogenesis. But it has not been documented in turtles or crocodilians. And this is actually where it gets a little interesting, right? So, crocodilians don't have sex chromosomes, right? They exhibit temperature sex determination. Temperature sex determination, we'll call it TSD, is a relatively straightforward concept. So instead of genetic inheritance like you or I have, where if we inherit genetic material from our father and our mother that determines what sex we are. Here, temperature sex determination, instead, if we put temperature on the y-axis, on the x-axis, let's put it in degrees Celsius, and then here on the y-axis we'll put proportion, I'll call it prop male. So this is the proportion of offspring that develop into males. What we find is that with crocodilians, they exhibit a female, male, female system, meaning that at lower temperatures of their range, you have predominantly female, but as the temperature increases, okay, because remember this is proportion male, so if there's a low proportion of males, that means there is a high proportion of females, and vice versa when you come over here. So let's just say this is 100%, and this down here is 0. So here the proportion of males is low. As temperature increases, you have a greater proportion of males up until some maxima, and then as temperature increases, it'll actually start to decline again. And eventually you have the more proportion of females. You could also draw this in the exact inverse. Let's see if we can do this live. So let's say this pink is the proportion females. It would be basically the exact opposite of the proportion males. As temperature increases, you have less and less females up until some minima, but then as temperature continues to increase, you eventually start seeing more and more females. Okay. So this is temperature sex determination in a nutshell. This is also found in the turtles. Like we mentioned, crocodilians do exhibit this system. Other taxa exhibit a more direct relationship, but this is a standard temperature sex determination in crocodilians. And that makes it interesting because if we look at, again, the common characteristics of this parthenogenesis, we see that the sex of the parthenogens is constrained by the species sex chromosome system, where XX females produce only female XX parthenogens. So because they don't have this sex determination system based off of chromosomes, this character doesn't apply. And so kind of the question is, well, how will they develop them? Like, what is going to happen? What will the organism look like? So, this was in captivity. Almost all parthenogens are found in captivity, just because of the nature of, one, it's very difficult to determine if an organism in the wild has parthenogenesis. It has been noted, but it's much more difficult. If you find a nest of eggs out in the wild, you're going to assume that it was a typical sexual reproductive event. But here, a clutch of 14 eggs was discovered in an 18-year-old American crocodile housed on public exhibition in Costa Rica. 7 of the eggs appeared to be fertile and were artificially incubated. After 3 months of incubation, the eggs had failed to hatch, and they were open to assess their contents. Out of the 7, 6 had contents that were not discernible, so basically didn't develop, but 1 found a fully formed, non-viable fetus that, upon dissection, was found to be female. So, if I remember right, they do list... so here, the eggs were incubated at 29 to 30 degrees Celsius, and the organism was female, which their system, temperatures below 30 degrees C and above 33 C produce females, 100% females. So this makes sense, right? It was still temperature sex determination. Because the temperatures were below 30, they developed into females. So there could have been a case for maybe the incubation could have been higher to see what they were going for, but I think the typical trend is to incubate at a lower temperature so that they have a little bit slower development. It's a little more controlled. I've seen it before where if you incubate at too high a temperature, the organisms develop too quickly, and that can lead to various defects. So I'm not sure if that's the reason why they did this here, but I just know that's what they do. And they typically do want to get females. So when you can choose males or females, particularly in a zoo or a conservation setting, you're typically going to go for females so that you can keep producing more offspring. Now, the cool thing was they took this little crocodilian parthenogen, and of course, I mean, this individual had been in captivity for 16 years? Yeah, so 16 years in isolation from other crocodilians. It was found when it was 2 years old. But you still want to do genetic testing because there is a concept such as sperm retention, when organisms can actually hold on to sperm and retain it for a long time before it can implant onto the egg. And there's always the case of, well, maybe another crocodile just got in there, did its thing and got out. So take genetics. And they did SNPs. SNPs are single nucleotide polymorphisms. Basically, they're a way to look more or less across an entire space of genetic material and find these small changes between individuals. And what they found is that the offspring has an identical genotype to the mother at greater than 99%. So if this were a sexual system, right? If this were a sexual system, we would expect the genetic materials to be half from the father and then half from the maternal lineage. So half, right? That's what you expect in a sexual system. But here they found that it was just basically 100% from the mother. That's what they found. So, of course, this signifies that it is parthenogenesis because they'd only inherited genetic material from one individual. And what they did also find was that there is a genome-wide maternal heterozygosity dropped dramatically. Now, I don't want to go too crazy in depth into heterozygosity, but see it as a metric of genetic diversity. Okay, if you have lots of, let's actually draw a little thing here. Let's say you have, so let's do heterozygosity. So we'll call this HO here, and we'll just say heterozygosity is the heterozygous. How many heterozygote genotypes do you have? So if you're an organism and you want to make sure that your diversity is maintained over time, let's actually just keep writing this out. A homozygote, right? Let's say an individual with 100% homozygote. They would look like this: AA, BB. Maybe they'll have the other little ones, CC. Let's just do DD. So this would be a completely homozygote individual. Heterozygote, let's show a completely heterozygote individual, would be A, maybe little a, big B, little b, big C, big D, little d. And this heterozygote individual has higher diversity because each of those letters, uppercase or lowercase, is a different type of gene. It's a different variation of the genes, right? So in this case, the homozygote individual really only has, here, let's do this, 4 types of genes. Let's just do gene variations to make sure it's clear, right? You have A, B, little c, little d. That's it. Those are the only 4 types. But in the heterozygote individual, right, what you find is 8 types. Instead, you have big A, big B, big C, big D, little d. Little d. There we go. So this is basic. This is like a very quick run through of heterozygosity. And what we can measure is the amount of heterozygote genes that you have in your genome. So that's really what the measure of heterozygosity is. In this case, there are more genes. But what they found is in the mother, the heterozygosity was 0.349, so about 35% of her genome was heterozygous, at least the genome they tested. But for the offspring, it's 0.045, a dramatic decrease. So there is a significant reduction in heterozygosity of the offspring. This is kind of what you'd expect. At least my first thought was this is what you'd expect because you are getting 100% of your genetic material from the mother. You cannot have heterozygosity because you're getting all your material from one parent. But it's something I didn't really think about this too much. They do say that in some types of facultative parthenogenesis, heterozygosity can exceed 33% of the mother, while some, where they're saying here, terminal fusion and central fusion, I still need to look those up a little bit more. So if you do know, please let me know down in the comments. But yeah, they said there are different cases where the heterozygosity can be remained quite high, but it always is much lower than the mother's. So it's either exceeds 33% of the mother's heterozygosity. So in this case, if the heterozygosity is 0.34, they would be looking at a heterozygosity of around 0.13 or something like that. So that's really it for this paper. There's a lot of extra information talking about parthenogenesis in other organisms. That the fact that there are very, very few Parthenogenesis records in the literature. But I just thought this was a really, really cool paper. I want to talk about it, and yeah, have a good day. If you like what I'm doing, please let me know, and suggest any articles. And I'm rambling right now, and that's fine because it is, wow, it is 6:30, and I don't know why I decided to make the video right now. Hey, what's up? I haven't had my coffee yet, partially because I'm out of coffee. Hi. Are you watching this? Are you watching this? That's cool, dude. Have a good one.